quantum space-time seminar speaker, and she's going to tell us about holographic landscape of symmetric product orbifolds. Over to you.
Very good. Thanks. Thanks for the invitation. I'm very happy to give this online seminar. Please interrupt me at any time if you have questions. I don't want to otherwise be just talking to my screen. But yeah, so let's get started. Okay, so the topic for today is this very long title, the holographic landscape of symmetric product orbifolds. Hopefully by the end of this talk, this title will make more sense because it sounds quite technical. But before I start explaining what the title is and all of its components, let me acknowledge my collaborators and the people behind this work. So we've been working on this for a couple of years, back from 2016 with Alex Bellin, Joao Gomez, and Christoph Keller. But most of the talk today is going to be focused on these last 3 papers, 2 from 2019 and this one from this year, from February. And in particular, I want to highlight, well, Alex and Christoph are also part of the collaboration. There's my PhD student, Beatrix Moman. She's going to be applying for postdocs again this fall. And in this last paper, it also involves Nathan Benjamin and Sarah Harrison. So if you're interested in following up, I hope that these last 3 papers will be the main part of it, but then some technical details are also in this 2018. I won't have too much time. Maybe if there's questions, the 2016 paper is mostly related to black holes, but I will say very little about black holes in this talk. So, okay, so let's get started. So what is the whole point here? So, okay, so preaching to the choir. ADS-CFT is this great tool that we have that provides a non-perturbative UV complete definition of what quantum gravity is. And usually, so we know, as we understand ADS-CFT, is that there are conditions on the CFT. So there are conditions such that it captures semi-classical gravitational features, okay? So usually we think about some large N limit, and there's a way which we expect this large N CFT to behave, and that's when we're going to start seeing the semi-classical gravitational features, have the weakly coupled description on the ADS side. Now, this is the lore behind ADS-CFT, but the question that we're trying to answer here, or start to sort of explore and understand what its features are, how do you go about basically building these conformal field theories that have these semi-classical gravitational features, okay? So what would be the set of conditions? How would I solve those conditions? What are the set of sufficient conditions for me to tell you this CFT will have the semi-classical gravitational features, okay? Now, today what we're going to do, so ideally we would like to answer this question in full generality in the whole context of ADS-CFT, but today we're going to focus on ADS-3 CFT2, okay? There's many aspects of this instance of the duality that are very powerful, and we're going to use them. But they're not everything that I'm going to say is going to be universal. So many of the things and the tools that I'll be using won't immediately extend to higher dimensions. But albeit that, I think this example still illustrates the challenges about how we go about identifying conformal field theories that have these semi-classical gravitational properties. So, okay, so what I'm going to do, we're basically going to divide this seminar into 3 parts, okay? We're going to explore 3 different doors. Each of these doors has its own kind of theme behind it. So the first thing that we're going to do, we're going to talk about holographic CFTs. So I'm going to basically describe what are the universal properties of the CFTs, what are the kind of the set of conditions that I want. Then we're going to discuss the strategy and basically what is the output of setting up the problem this way. So as I said, so from the holographic CFTs, basically what we'll discuss is a set of necessary conditions, okay? So I'll tell you what are, for the purposes of this talk and the work that we did, what were the conditions that we're imposing in the CFT. By the time that we reach the end of this seminar, you should be thinking, was that sufficient or not? Okay, so this is the part that we should keep in mind as this program evolves. We'll only be imposing what we consider, what we can, basically, the necessary conditions, but the holy grail are these sufficient conditions or not. Then comes the strategy. So we don't know what all the space of conformal field theories are, not in 2 dimensions, not in higher dimensions. This is understanding the space of theories is quite a difficult question. So we will have to make some compromises. And this is where symmetric products are going to appear. So I'm going to focus on a certain class of conformal field theories in 2 dimensions. So this will be just some subspace of all possible conformal field theories. And I'm also going to start here restricting the analysis to supersymmetric states, okay? But this is going to define for me the portion of this landscape. Okay, what are the class of theories that we're going to consider our universe? And then within that universe, how we're going to go about imposing these necessary conditions. And the punchline of this talk will be the output, and it will be that we will find interesting answers. It will be a little bit, I hope that I'll illustrate that it will look like finding needles in a haystack. So it was a bit challenging to find these CFTs, even with this approach, even within the subset, but we managed to identify all possible candidates. And well, hopefully I will not run out of time, but at the end of the day, the theories that will make a prominent appearance are minimal models in this construction, as I will illustrate as we go along, okay? But that basically will be the punchline. We do find a whole landscape, it's beautiful, and I hope I explained to you what these theories look like. Okay, so very good. So let's start by describing what are these necessary conditions, okay? So what are these holographic CFTs? Okay, so what I have in mind is nothing like exotic or extravagant, okay? So when I say semi-classical gravitational features in the context of ADS3 CFT2, I really have in mind that I have a theory of 3 dimensions, ADS3, that will have a part here that will be the Einstein-Hilbert action. And there will be some matter that usually you can think of it as being like some fermions and some scalars and some gauge fields, whatever like massless sector that you want, okay? So this is the low energy effective description from the point of view of the gravitational theory, okay? You can, and for the purposes as we go along in this talk, this part here will be some sugrav, like, because I will be using supersymmetry, think of it as like, okay, this will be some supergravity, some low energy supergravity description.
And Alejandra, you require the spectrum of your matter to be independent of G Newton. Is this right? Independent of N?
Yes, yes, independent of G Newton. Yeah, so there will be also like a 1 over G Newton out here. Usually in the supergravity, like everything will come like that, but it will be some massless, like, yeah, it will not depend
But
on.
the number of states should not depend on C.
Exactly, yes, 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 because I want this to be a good effective field theory. So I don't want the number of states to scale with G Newton, because then my local description that I'm writing here breaks down. So indeed. So that's why nothing exotic, like I do really want to describe something that will look like some nice theory, some semi-classical theory that we tend to discuss in this.
Sorry, so for instance, this Gopagopar-Gaberdial Vasiliev kind of dual would not fall in your cap.
No, that's not, I'm not considering higher spin theories.
Right.
So it only goes up to spin 2 and lower. So that's why, like, yeah, I can have spin 3/2, I can have spin 1/2, but yeah, no, nothing higher than spin 2. In the massless part of the spectrum.
Yeah, but I was thinking even about massive, the fact that they have these light states whose spectrum is governed by N.
Yes, but I really don't want that.
You don't want that. Yes, thank you.
I don't want that. So yeah. So higher spin theories do not fall into this bucket. definitely they won't. And actually, I don't like that feature that there were too many light scalars. I would not have considered that as a healthy, like semi-classical, like gravitational theory a la Einstein, Hilbert. Those type of theories tend to not have a good description as like this being the starting point. So that's why they're not included in here. But okay, so within this classes of theories, the theories of 3D gravities, there's some universal properties that all of them share. So there are light states, but not the ones that Shiraz was describing. So here, the perturbative states that I'm thinking are basically like the Brown-Henault boundary gravitons. Those will appear in here. And there will be perturbative excitations that are not growing with G Newton, that are coming like from the matter sector. So like some like wiggles that the matter fields that a scalar will be doing inside of the bulk. There's also in this theory of ADS-3 gravity, there always will be a black hole. There's always going to be the BT set black hole as a solution in this theory. And well, depending on what you put in here, and basically if from a string theory point of view, how did you get to this theory from a higher dimensional context? There will be other stuff, like there can be like multi-center configurations, or like from a higher point of view, they will look like multi-center configurations. From a lower dimensional point of view, they will look like conical defects and stuff like that. But that's very theory specific, and I'm not going to impose any condition on that part of the spectrum. So I'm going to ignore it today because it will depend a lot on what I'm saying here. It's not that it's not interesting, but it tends to not be universal, at least to our understanding of ADS-3 CFT2. And one of the things, so in this universal classes of theories of gravity, one of the very, very universal entries in the dictionary is the central charge, the Brown-Henault central charge, which is basically written down here. So the central charge of the CFT is the ADS radius and Planck units, and this number has to be very big. So if you want, you can say that this is my first necessary condition, that I'm looking for CFTs that have very large central charge. But okay, but more refined than that, besides saying, okay, I want CFTs with large central charge, there will be two other conditions that we're going to discuss, okay? They're not fully independent conditions, but I do want to make a little bit of a distinction between the two of them. So there will be one that we're going to call the black hole regime, and another that I'm going to call more like the perturbative regime. How do we impose restrictions on those two sectors? So, okay, so let's talk about the black hole regime. So we will have a BT set black hole that has basically a large horizon, so a large area in units of Planck length. If you go through the ADS CFT dictionary, this basically tells you that you have states of energy comparable to the central charge, and they're very, very big. And one of the most famous results from like the first years of ADS CFT was the result by Strominger and Waffa, and then also Strominger that generalized it more broadly. And it was, how do you describe the entropy of the black hole in terms of microstates of the dual CFT2? And so basically, so the claim in ADS CFT is that the entropy of the black hole is the logarithm of the number of microstates, and the CFT from going from this step to this other step is basically dictated. So the easiest way to get this formula is via some modular transformation, which is known in our community as the Cardy formula, or more in the mathematics, it will be called the Hardy-Ramanujan formula, the Rademacher asymptotic expansions that tell you that at high energies, the number of states goes like the square root of C times E. And then from this step to this step, you're just using the ADS CFT dictionary. And as we all know, this perfectly agrees at this leading order. The Cardy formula captures basically the black hole entropy with all the numbers in the right place. But here is where this is not quite enough. So I do want to make a distinction that from going from this point to this point, which was given by this Cardy formula, this is universal in the CFTs. It seemed like I didn't impose any restriction on the CFT itself, but actually this step only holds for E much bigger than 1, and C fixed. And this is different. So this part over here is different than that condition that I'm imposing there. So we do have black holes. So you could have black holes that are in this regime, but there are also black holes that are in this regime as well when E is similar to C. And so the Cardy formula doesn't quite capture everything. It's needed. It tells you that the dictionary is compatible. It's viewed as a necessary condition for the whole ADS CFT program to work. But not any CFT is going to give you this beautiful result and this match in this range of parameters. And so that's what people impose as a condition, that you need an extended Cardy regime. Okay, so this is what people usually in this community, people working in this area, call the extended Cardy regime, that you're not quite satisfied with this. You really want to capture the black hole entropy in the full extent of parameters. Okay, so this is viewed as a condition.
Sorry, Alejandra, if I said this in terms of temperatures, is it right to say that the Cardy formula only guarantees this behavior at very high temperatures?
Exactly, exactly. So this implies that temperatures are very, very high. And this here tells you that you should be able to go to temperatures of order 1, down up to the Hawking-Page transition. So the black hole is a stable solution up to temperatures of basically order 1/2 pi, or it depends on how you impose units.
Sorry, and how do we know for sure that the black hole, I mean, we know the black hole exists, but how do we know it's the dominant solution immediately above 1/2 pi?
Well, this is where the details start mattering. So that's why I'm being a little bit here. I'm being kind of like, I didn't quite put like the number precisely, and I'm saying like, oh, it's just order. Because this is where the conical defects and these other multi-center solutions might basically can give you some like window that people would call enigmatic, that maybe some other saddle point dominates. But usually, at least in most of the theories that, and then a lot of like the supergravity-like theories in ADS3, the black hole still tends to dominate for a long period of time. So what you do is that you compute the free energy of these solutions and then start comparing them. And yeah, there could be circumstances where other solutions close to this temperature, when you're getting closer to the Hawking-Page kind of phase transition point, they might dominate over the black hole. But it's still not enough to say that there still will be a mismatch between these two, broadly speaking, between these two things. So that's why I was also putting here just an order C, because it will depend on the theory. If you say, oh, is it C/12? That's if you don't have any conical defects, or maybe it might be a different number because there are some enigmatic states that are dominating. And so this is where the details of the theory will tell you how, like precisely until what point the black hole dominates.
Sorry, just to be, I mean, probably a little anal here, but just to be totally clear, is there a clear argument that there is some number, that for temperatures above some number of order 1, whether 1/2 pi or not, let's say 1,000 times over 2 pi, that the black hole must be the dominant saddle point above that temperature? Is it clear, or could it be just that the black hole never dominates?
Oh, that the black hole never dominates. Oof. I've never encountered that, but
I also think it's very unlikely, but I was wondering whether there was
yeah, well, in some sense, okay, let's put it this way. So there will be some temperature of, like, right, it might be like 1,000,000 or 1,000 or whatever number you want. But if you have a theory that is modular invariant, and there's a gap in the spectrum, however small it is, but there's a gap between the vacuum state and the next excited state, this is always going to be universal. So the modular properties of the CFT assure to you that there will be at least some sufficiently large energy for which you're going to get the square root behavior. And it is nicely described by the Bekenstein-Hawking entropy. So the black hole will dominate, yeah, probably, as you're phrasing it, it's a matter of okay, how big this E has to be. And in the best case scenarios, this E can basically be comparable to C. So you can go down to temperatures of order like this 2 pi. But yeah, then maybe it gets a little bit pushed up, or maybe pushed up a lot if you have way too much stuff. But this is always going to be there. So if you want there's always going to be a black hole. Unless you have an alternative way of how to account for the Carty formula without using this area law, but that I'm not aware of.
Thank you.
Yeah. But okay, so very good. So this is this extended Carty regime is a condition on the spectrum of the CFT, and something that happened several years ago, back 2013 or so, is that what they notice is that this black hole regime already puts restrictions on perturbative states. So here by perturbative states, I'm thinking of what we're going to be calling light, very schematic for now. It's just basically states that have energies that are of order 1 in Planck units, so they don't have energies that scale with G Newton. That's what I'm calling perturbative. And this requirement of having a black hole that dominates for beyond what you expect from the Carty formula already tells you something about this perturbative regime. And so, for instance, these authors here, they basically said, oh, we want to have a Hawking-Page transition. So if you want to have a Hawking-Page transition, requiring that you have a black hole that dominates up to the Hawking-Page temperature actually will put in conditions on this perturbative part. You can also phrase it in terms of BPS black holes, that if you have a supersymmetric black hole in this theory, and it will carry a lot of entropy, it will also put conditions on the light part of the BPS spectrum. So it works both at finite temperature and at zero temperature.
So is the existence of a single Hawking-Page transition one of the conditions you will put, or is that not necessary?
The easiest way how to phrase it, it's a single Hawking-Page transition. Like if you want to see immediately how the things are constrained, you would put it as a single Hawking-Page transition, but they do discuss how you would do it if you have like basically different saddles dominating throughout. And the endpoint is roughly the same. Like, because they're doing some gross estimate about what is the maximum that you're going to tolerate that I'll explain in a second. But
okay, thank you.
Well, I'm not going to explain how they derived it, but I'll just say what the final result is, because otherwise I will definitely be talking for like 3 hours. But yeah, they do account for the fact that you could have some other saddle points in this middle range, and that's explained. To some extent, they acknowledge that in this paper here. Okay, but very good. So let's talk a little bit more about this perturbative regime. So what do we expect out of this light states? And so let me phrase it, because it will be useful for what I'm going to talk about a bit after. Let's talk, like, let me put myself on my string theory hat and think about like, okay, what do I expect when I have some string compactification? And I tell you that I want to describe the spectrum of states, like roughly, I'll be super hand wavy, but I just want to give you an idea of where we're coming from. So basically, from a string theorist point of view, what are my expectations, or basically, how would we go about building some effective field theory description? So usually, not always, but in many, like compactification, many string theory setups, there will be 3 scales. There will be the Planck scale, we will have a string scale, and we will have some ADS scale, okay? That will define basically how our effective description will look like, okay? We don't always have these 3 scales, but let me just, it's easier to describe what's going on if I put in here these 3 scales. Okay, so let's first discuss what happens if, for instance, the string scale is very close to the ADS scale. Okay, so these 2 things are basically the same. Okay, so this is what I would be calling, like in the jargon that I'm going to be using later, this will be some weakly coupled regime. So some very like stringy regime is the regime, for instance, that currently like Rajesh with Matthias and Lawrence are discussing when they're solving for ADS3 CFT2. They're in a regime where a lambda string is basically very similar to lambda ADS. Sorry, was there a question? No, okay. So that's basically our very, very stringy regime. And in that case, the expectations that you have is that when you have states of some conformal dimension h, where I'm measuring, basically I'm relating the conformal dimension to some energy in ADS units. The expectation that we have here is that the number of states when the energy is big in ADS scale, so well, basically string scale, they're the same in this context, in this discussion, so you expect the number of states to go like Hagen, okay? To grow what I'll be calling for the rest of the talk, if I refer to some fast growth, I'll be basically referring to this Hagen-Norton growth, okay? Now, the thing that is interesting here is that this is enough to meet the black hole regime. So if you have basically this number of states, so if the light part of the spectrum, so states that are not growing, so these states are not growing with Planck length, but basically if you have this states like here, then this will imply that the S of the black hole will satisfy this S of Carty that I was explaining in this black hole regime part. And so that's what basically these authors, Hartmann, Keller, and Stoika showed, that if you had Hagen-Norton growth, that was enough to assure that you had a Hawking-Page transition, okay? So that was the maximum that you could tolerate.
Sorry, Hagen-Norton growth with some bound on this coefficient of growth.
Yeah, CH. CH is basically, so CH is basically something that, like, when the string scale is exactly the same as it, like when it's exactly the same as the ADS scale, like it's basically 2 pi. It can't exceed 2 pi, basically, but it could be a number smaller than 2 pi, and I will still call that like Hagen-Norton. But basically CH has to be less or equal to 2 pi.
And is it right that if CH is larger than 2 pi, then you're guaranteed that there can't be just a single Hawking-Page transition? Something would have to come about in the middle.
If this is violated, then you're not going to have a phase transition, yes.
But you could still have what you might reasonably call the gravity dual description, or not?
Well, this, I'm not going to call, for me, this is a very stringy description. So I would not call it gravity in terms of like having an Einstein-Hilbert.
Okay, what you might reasonably call the weakly coupled stringy description.
Exactly. I will call it like a weakly coupled stringy description. You can aim for some roll sheet description of this, and like I'm trying to understand what is a D-brane system.
Right. What I was asking was that suppose CH was larger than 2 pi, it was 4 pi, would that still be conceivably consistent with a weakly coupled stringy description?
No.
Why not?
Because I think you will have divergences in the free energy that I think are just, I thought my understanding, but maybe
temperature. The divergence would be at temperature half times the Hawking-Page transition, which would tell you that the perturbative phase is not stable above that temperature. Something else would have to kick in. What's wrong with that?
Well, yeah, to be honest, okay. This is that I was thinking about it from a string theory point of view, that I don't know of a string theory that will allow you to have bigger than 2 pi. Maybe there's some other description, but definitely I don't see how string states could do that.
Yeah, that probably is that's probably an argument. I just don't see it.
Yeah, so that's why we kind of like say, okay, Hagen-Norton is as much as we will tolerate. So let's not talk with this.
Yeah, I was also agreeing to look at Hagen-Norton. I was just wondering about this bound on the coefficient.
Well, when they actually put this condition on the Hawking-Page transition, that they want this discontinuity in the free energy, the 2 pi comes from free. So they didn't like impose it.
But that presumably demands just having a single Hawking-Page transition. Right? I think it's clear that if you want a single Hawking-Page transition, this had to work, because the perturbative phase.
But then if you have more, then I think it's a weaker bound. So it will make it smaller. So I don't think it will allow you to have more.
Okay, I'm sorry. I don't see it, but please.
Yeah, okay, it's a good point. To be honest, I'm not going to, but my intuition was that if they, no, but okay. No, let me think, it's a good question.
Could I just take half a minute to say that, you see, what goes wrong is that if you're at temperature that is above a critical temperature, if you've got this Hagen-Norton growth, you get a divergent partition function in the low energy phase. Now, C is larger, that brings that temperature down, right? That critical temperature down. So you will not be able to go all the way to Hawking page. That's clear. Because if C was 2 pi, you could go all the way to Hawking page without having this. So something else would have to intervene. But it doesn't seem clear to me that there couldn't be some other phase, which is not immediately the black hole in the middle. But I don't want to disrupt. So
Okay. No, thanks, Shiraz. But yeah, but for the purpose of today, like because we're trying to basically understand what will be the string or dual descriptions, and so I am not going to go above Hagedorn because then I will be very lost on what's going. But actually, this is not what I want to impose. I don't want to look for theories that have Hagedorn growth. I want something different because what I want is to have a separation of scales. So I want the string scale to be parametrically larger than the ADS scale. And this is basically, so this condition here is where I'm in this, what at the beginning of this seminar, I was talking about the semi-classical gravitational description. Okay, so this is where I have like a big difference between the string scale and the ADS scale. I can talk about this low energy effective description in terms, or I can try to talk about this low energy description in terms of some supergravity-like theory, where I have this hierarchy between these two parameters. And in that case, so basically, given that Hagedorn was as much as I was going to tolerate in the previous slide, then from that point of view, if now I'm in this other scale, so again, I'm going to be measuring the conformal weights in terms of their energy and ADS units. Now I want this power here to have this H to the gamma, to have a gamma that is much less than, sorry, not much, basically a gamma that is less than 1, okay? So Hagedorn was when this parameter was equal to 1. Now what I want to, when I have the separations of scales, what I would like is for this number to go down so that the states that are very energetic in ADS units are actually separated from the stringy states, from this whole tower of massive string states. There's a separation between them. So I basically will have some low energy number of states and then some high energy, some stringy states that are up there, but I don't care. I will have some effective description for these ones, and then there will be more stuff basically above. And this basically, this gamma here, so if I think, so just to give you some example of like what I expect this gamma to be. So if I have some compactification, since I'm talking about ADS3, let me just put here ADS3 times some compact manifold like this. You don't have to put the 3, it doesn't matter. But basically what we will have in the back of our mind is that we want some form of like bulk effective description where we basically don't want, like this gamma, like in terms of these perturbative states, will be like, okay, how many states can you fit in a box of dimension D? And so then gamma will tell you, gamma will just basically be D minus 1 over D, which tells you that you will allow the free energy of the system to go like T to the D, okay, for these perturbative states. So this is basically telling you, like, look, and when you're in this regime, so when you're around the scale down here, basically you will have some effective description, which for the perturbative part of the spectrum will look like putting like fields inside of this box, where the box is basically this space-time, okay? So that's what we have in mind, that this guy, and that's why this number over here is clearly strictly less than 1. And so that will be our criteria, that as we look for CFTs and we look at their spectrum of operators that scale according to this rule, we will want this type of growth. And this is what I'm going to call slow, okay? So Hagedorn was fast growth, it was much more states. But if I'm looking for some supergravity-like description, a minimum requirement that I will need is that I don't exceed, I'm below that. And so this is the version of us demanding that we don't have all the stringy states. Okay, very good. So that's the way that we're thinking about this. So let me just, oh, sorry, I had it repeated twice. So from this point of view, let's now think about, okay, so how are we dividing this space of CFT? So as we're trying, given all these conditions that we talked and these expectations that we had about the spectrum, the idea is roughly the following. So we have some space of conformal field theories, okay, abstractly. And in some sense, what we're trying to carve out of that space of conformal field theories, what is the space of like what I will call holographic conformal field theories. And so what I'm demanding here is that, okay, as we said, there should be a large central charge. So in the space of conformal field theories, I want to be capable of taking C to be large. And then the two necessary conditions that we discussed, although they were not fully independent, was basically this black hole regime where I told you we wanted this extended Carty regime, but I want actually something stronger than that because this is still compatible with Hagendorn and I don't want the Hagendorn growth. Actually, what we want, what is more stringent, what will restrict us most, is that if we look at the perturbative part of the CFT spectrum, is that we want basically slow growth, okay? So this will be the most important condition that we'll be imposing. I'm just, because I'm a black hole fan, I will keep on writing number one, but number two is basically the stronger condition that I really don't want to have states that will be kind of growing exponentially with the conformal dimension, the number of states, the degeneracy of states. Okay, very good. So that's where we are right now in terms of like, what are these necessary conditions? What are we going to roughly be calling at this stage a holographic CFT? Very good. So I want to find at least some subset of what are these holographic CFTs. I want to build them. So these are the conditions. Let's go about designing the theories. So we'll start talking about the symmetric product orbifolds. Very good. So we wanted CFTs with large central charge, and we basically want to have very good control on the spectrum of the CFTs, because otherwise we can't impose this condition. So we need to have control on the spectrum of the theory so we can impose these necessary conditions. So one type of theories, so for instance, if you just wanted to enlarge the central charge, is basically do what people call a symmetric product orbifold. And this is basically a very simple procedure that many of you probably have encountered in string theory life. So let's say if you have a theory with central charge C, and then what I'm doing here is basically tensoring at m times. So that's what I'm illustrating in this point here, and then modding out by the symmetric product, basically by the permutation group. So I'm modding out by the permutation group here. This is a very good way how to increase the central charge, because if this theory has central charge C, then this one will have central charge C will go to m times C. Or let me call this one C naught. This one is C naught, okay? And then I'll write equal sign. Okay, so this is a very good way how to increase, if you have one favorite theory, then if you want to find something that has a large central charge, you can do this operation. So the first one, the series C here, I'll be calling it the seed. Okay, so it's the input in the symmetric product. You give me one, you tensor it, you get your family of large CFTs. Now, one of the reasons why these theories are very nice, there's many of them, but one of them is because you do have a lot of control on their spectrum. So there's this formula known as the Dijkgraaf-Moore-Verlinde formula that basically tells you that if you know the spectrum of this theory, so basically is this number, this D of n for the seed, then you basically will know what the spectrum of the nth copy of this procedure is. And that's what this long change of formulas here illustrates. So you basically build some grand canonical partition function where you're now adding, averaging, or adding a fugacity for each mth symmetric product. And the things that these authors showed is that the sum beautifully can be written as a product formula. And this product formula, like this illustrates very clearly that if you know what the degeneracies of the seed are, then you basically, from here, you can extract the degeneracy of any of these guys. So that's very nice. So you have a lot of control on the spectrum based on the fact that you know what the C does. But there's a problem with this theory. And so something that one of my collaborators showed again a long time ago in 2011, well, which was not super surprising, is that if we now, for these theories, all of, so basically one of the things that Christoph showed is that all of like this symmetric product theories, basically have Hagendorn growth. So they're fast. So if you look at what we were calling at these states that had E much bigger than lambda ADS, basically states that have a large conformal dimension but are not growing with a central charge, they're all Hagendorn. So they're the type of theories that I told you I didn't want it to discuss. I did not want it to discuss basically Hagendorn type theories, but all of these symmetric products are Hagendorn-like. And there's nothing that you can do to shake this off. Okay, you construct a symmetric product. Maybe the 2 pi might be not exactly 2 pi. It will be at most 2 pi, but it could be smaller. But basically they will all have exponential growth. And so it's like, okay, so these are clearly what I would have called like holographic CFTs according to my definition a few slides back. And so, okay, great. So I'm studying the NT set. That's not what, let's not give up there, because these constructions, these symmetric product constructions appear quite a lot in our string theory literature. They appear in the D1, D5 system, for instance, and other like examples of ADS3 CFT2. And so what's the story there? So what I'm thinking of, is that basically the symmetric product description, you will think that you have some moduli space of CFTs. So there will be a class of basically this little cloud here is depicting a space of CFTs that are connected and by a moduli, and by a moduli I mean a space of marginal deformations. So basically I will have some marginal operator in the space of CFTs, and the symmetric product description is one point in this moduli space, is what I will call the weakly coupled point. So it's a point where the string scale is basically the ADS scale. But if I have a marginal operator that turns on for me a coupling that will allow me to reach a point of strong coupling ideally, where basically then the string scale is much bigger than the ADS scale. And that's what we have in mind, that maybe, okay, you start with a symmetric product theory, okay, which will be this weakly coupled description. So basically the copies are not talking among each other. In that sense, they're weakly coupled. But if I have a marginal operator, basically I can potentially, it will introduce a coupling for me, and I could move away from that point and find my strongly coupled point, where here, in this point over here is where I expect to have the gravitational description, okay? Now, so one way that we can phrase this then is say, okay, we want to then look for symmetric product theories that have marginal deformations that basically have a moduli space. And then maybe that can be a signal of things going well. Now, I don't want to, so we will look for that basically. So our hope, given that I decided to study symmetric product theories, the only hope that I have at this point is to basically think, okay, I will have to add some marginal deformation. This will basically modify the theory, and it will make it move in this moduli space. It will make this spectrum look more sparse. It will basically make it go from fast to slow. But what I don't want to do at this moment today is to actually study like the effect of this marginal operator. I want this marginal operator to exist, but this is where we will start kind of like cheating a bit or using our best knowledge, we'll say, okay, let's focus on quantities that are protected basically under this, this flow, under this deformation. And those quantities that are protected, they should already have, because they will not depend on the coupling, they should have these gravitational features. And so this is where supersymmetry comes in. So we'll look at BPS, or basically supersymmetric quantities that are protected. Because these are quantities that we know that will not depend on the marginal operator. So if these quantities, so if this whole program is actually useful, that I can think of like, okay, I have a weakly coupled description in terms of a symmetric product and I have this deformation, the BPS quantities should already have those gravitational features in them, okay? If they don't, then it means that there will be no point in this moduli space. Well, I would have a nice strongly coupled description that will have this gravitational properties that I want. So the BPS part should already have this information in it. So that's what we're going to focus on first, okay? So we're going to try to implement this condition on protected quantities.
Alejandra?
Yes.
For your purposes, it would also work if the theory has a relevant operator, right?
Yeah, but okay, I like marginal because it keeps on making it a CFT. So my moduli space is, yeah, I guess you can also, I don't know. These theories, actually the ones that I'm going to describe towards the end, they actually do have relevant operators as well. But in order to, basically here I'm thinking, I want to be basically as similar as D1, D5 in some sense. And so I want to have a marginal operator.
So it also needs to be exactly marginal.
Yes, it will be a BPS operator. Well, it will preserve supersymmetry. And so along this moduli space, I will preserve supersymmetry and I will preserve conformal invariance.
No, but a BPS marginal operator need not mean exactly marginal, right? Because it could recombine into some other short multiplet to become a long multiplet.
Well, the ones that we're going to build are going to be exactly BPS.
Excuse me, sorry?
The ones that, as I discussed, the space of marginal operators, they're protected, or at least to my understanding.
I see. So you're saying that there is no recombination also that could happen?
No, not as far as when I learned about this, my understanding was that these operators were always, we didn't at least have any evidence that they were not going to be, where they're going to lose their supersymmetry. They're going to be BPS throughout.
Okay.
Yeah.
Thank you.
Yeah, you of course could describe other moduli spaces and do other things, but this is at least the space of things that I'm going to do. So it's not the full space of things that one could do, but it's what we're going to consider.
So following up on Abhijit's question, is there some sort of index one can compute that is protected through the flow for a supersymmetric algebraic flow?
Edwin, the elliptic genera.
So that's when you have a marginal deformation. But suppose you had a relevant deformation, is there still an index one can compute?
I don't, that's why I was a little bit shaky, because I don't know. I haven't studied what happens under relevant deformations. So I don't know if the,
so
I know. Yes?
No, I was just going to comment that in 4 dimensions you can. I mean, I think in 2 dimensions also you are symmetry after the RG flow.
And then something like this, like the elliptic genera, will be protected?
Yeah. You could do that. In fact, the way you would compute the elliptic genus of minimal models from a Landau-Ginzburg point of view, that's how you would do it. Because, you know, the minimal model also you would, the Landau-Ginzburg point of view, you start with a scalar field and then, I mean, a chiral multiplet, and then you deform it by some superpotential, right? So that's a relevant operator.
Okay.
And then you can follow that and compute the elliptic genus.
And Abhijit, then you compute the R charges by some sort of extremization. You
Yeah.
compute function of possible
Yeah,
R
I
charges.
mean, when it is needed, when there is an abelian symmetry, then you would need some sort of extremization. If there is no abelian symmetry, then the requiring superpotential to be marginal fixes it.
I see.
Right. So then this suggests a possible generalization to what Alejandra is going to tell us about, right? Because
Yeah, that's what I was indicating.
No, that would be interesting. I never, and because we were trying to follow D1, D5, I'd never seen discussions, at least in this, in the context of CFT2s, of describing holographic setups where they were built out of relevant deformation. But yeah, no, that's this kind of illustrates that we have not really explored very much this space of CFTs from this perspective. But this is interesting. So let me.
Can I just ask something? I mean, if you have a relevant deformation, will it not change the central charge? How do you know that the central charge will remain large?
That's a good, that's a question for Abhijit.
But Ashok, couldn't you read off the central charge from the, if you can compute an index, you could just read it off from the calculation and check whether it remains large or not.
Yeah, I mean, from rather than from the index, you could just come. If you are able to identify the R symmetry, the supersymmetry will relate the R symmetry anomaly to the central charge. So you could compute it and check what it is.
But we know that the marginal deformation is going to change the central charge, right? So if you could read out the index without knowing the details of the deformation, how will it work?
Sorry, for the marginal.
Why is the marginal deformation changing the central charge?
Sorry, not marginal, relevant deformation.
Right.
Yeah.
So I think this will come about, my thought was that this would come about from the extremization procedure. You do it as a function of some trial R charges, and then you do some extremization.
Okay.
Right.
Still scales, but then, well, but it's still like.
Right.
It's a
You
little
need to
like
know
the
the
free
full
energy
R.
works in 3 dimensions, the R symmetries of chiral operators are obtained by taking this sphere partition function and then extremizing with respect to the central charge. And the sphere partition function plays the role of a central charge. Extremizing with respect to our charges.
In 2 dimensions, what is being extremized is the trial central charge, which is again computed as a Tooft anomaly in the R symmetry. So it's simpler to compute.
And it's a precise analogy to what happens in 3 dimensions, because the free energy on the sphere is the thing that increases under RG flows, right?
Okay. So you have to know the full RG flow, not just existence of a relevant deformation, right?
No, I think that you compute some sort of free energy at basically the free point, but as a function of potentially renormalized R charges, and then extremize that free energy with respect to the R charges.
I mean, I think the way you would do it is more simply is to require that at the fixed point, the operator that you have turning on is marginal, and then fixing the R symmetry from there when there is no accidental abelian symmetry. And then once you fix the R symmetry, then you can compute the central charge.
Right. And then if there's an accidental symmetry, you need to do more, right?
Yeah.
Yeah, but you still have, it feels like you have to know a lot about what this relevant deformation is. Well, not a lot, but at least what's happening to it.
No, as Abhijit said, I mean, at least in 4 dimensions, there are examples where people computed the Witten index, the superconformal index of Seiberg dual theories. Starting from free description.
Okay.
The conformal field theories in the IR, in the UV, they're, asymptotically free theories. And yet people computed the full superconformal index of the IR theory very simply using an effectively free description and then extremizing with respect to potential R charges.
I mean, even in 2 dimensions, we computed the index. Even in 2 dimensions, we computed the index of 0,2 theories, for example, gauge theories, in the same way.
I see. Okay.
From the free field description.
Ashok, do you see a problem in this?
No, there is a problem with this, but it could be that in principle, the marginal operator will take you all the way to C equal to 0, right?
It could be.
You have to make sure that doesn't happen, that you have to.
Theories where that doesn't
Yes.
Yeah. Okay.
Yes.
Yeah.
Okay.
Yeah, I would just like to add one more comment. One more complication in this kind of thing is, of course, that you can have like decoupled sectors, which you should be careful about. But
yeah, some free theorists can decouple, right? And those will, then you have to redo the whole analysis after decoupling.
So in principle,
And the relevant case, Loga, no?
Yeah.
Yeah. In the relevant case, and in principle, I mean, they can take away all the asymmetry, and then you might be ending up with some free theory.
But that
Yeah,
is,
in 4 dimensions, at least there is a prescription about how to handle this kind of thing.
Yes,
I
it
would-
can be
there
done.
is a similar-
I'm not saying it cannot
Sorry?
be done. I'm just saying it should be something that one should be wary of.
Yeah, if one hits unitarity bound, then you decouple that operator and so on.
Yes, exactly. Yeah.
Okay. Very good. So I'll proceed. But today I'm only going to look for marginal operators. I'll keep it on the safe zone. But these are very interesting comments.
Sorry, I just had a slightly different question. So when you're just talking about marginal operators, of course you can have theories where you get to strong coupling, but not by quite a marginal operator. But like what happens, let's say in Chern-Simons theories, that you have a K, and you're kind of increasing it in discrete amounts. And maybe the 2D analog would be probably some Bezier-Witten theories or something where you have some number which are increasing in discrete amounts rather than slowly deforming. Do you think that your analysis would take that into account, that kind of cases also into account, or you're kind of?
I'm not sure. Like we really were thinking of it in terms of a marginal operator, because we're basically thinking of something that, since we started with the symmetric product construction, we wanted something that made the copies interact. So that for us, this was the natural way how to like describe this. Like, okay, let's not have like just n copies of theories that are not talking to each other, basically, and make them talk to each other. There might be a different mechanism, and I don't know if, because we haven't really studied, like at this stage today, we haven't studied what is the effect of the marginal operator at the level that I want, that I'll maybe, if I have the time, since it's already been an hour, to say a bit of like what we would like to see in terms of effects. But what I can say, since I'm getting ahead of myself, there will be different types of marginal operators in these constructions. There will be single trace and multi-trace, and all of them have different effects in terms of what they would do to the strongly coupled point. So like the single trace marginal operators will basically lift the conformal dimension, will basically introduce anomalous dimensions to the operators, which basically tells you all these, potentially these currents will get lifted. But then there's also multi-trace marginal operators that could introduce basically other types of couplings. They can change couplings and higher point functions. So they will change parameters in this like 2D supergravity description. And maybe you could interpret them as these other effects, but we haven't explored all of these possibilities. But there's a lot of things, like the space of marginal operators that we're finding here, it's more rich than the one that you find in D1, D5.
Okay.
So.
Okay, thanks.
Yeah. Okay, but okay, it's been an hour, and so I should kind of be wrapping up. But okay, but let's discuss a bit more. So sorry, I wanted to just say here. So yeah, I guess very quickly. So basically, yeah, so we were looking just to refine a bit more based on this discussion on what I'm calling a holographic CFT for the purposes of today, is that basically I'll be looking at these protected quantities that have gravitational features. And my third condition is that within this holographic CFTs that I have a marginal BPS operators, okay? So it's basically, I decided to study at the space of this like symmetric product theories, and now the question is there an intersection between the space of symmetric product theories and the space of basically holographic CFTs? Very good. So what is the protected quantity that I'll look at? So as we were talking about, I'll look at the elliptic genera, which is basically the trace in the Ramon sector of -1 to the f. And in the mathematics context, this is a weak Jacobi form of index T, okay? So what we'll do here is basically do the symmetric product orbifold of the elliptic genera. So the formula will be very similar to the one that we described before. Here, just because it's convenient, so this parameter here was what I was calling before M, but the thing is that the index naturally goes into that prefactor. So now I have like R copies instead of M copies, but it's basically the same thing. I'm annoying, I like to change notation. But yeah, so we'll do the symmetric product of the elliptic genus. This is protected. And so what we'll be looking for then is that as we go to the NS sector, so this quantity originally, so we first build it up in the Ramon sector, then we will go to the NS sector, and what we'll impose in the NS sector is that the number of light states basically has this property here, this slow, this is what we were calling the slow growth, okay? So this will be our necessary condition, and as a protected quantity, it should satisfy. Like if there is a hope of this theory to have a gravitational description, this protected quantity should already reflect this. So just to reiterate again, we're not looking at the partition function because that already will have this gamma equal to 1, but the elliptic genus has cancellations, and it could basically tell us something about how the theory behaves away from the symmetric product, and that's why the growth can potentially be lower. It doesn't have to be lower. It could also, and in most cases, gamma will still be equal to 1. So there will not be enough cancellations. That's usually what happens generically, but there's a hope that maybe there are cancellations in this object. And the spoiler is that we'll be able to identify which are, so from this mathematical point of view, the first thing that we'll do is identify the Jacobi forms of the seed that basically will lead to a behavior. So this infinity, sorry, I didn't mention, this infinity here means C going to infinity, so the large C limit, that we will be able to identify the Jacobi forms in the seed that will lead to this basically slow behavior of the number of states in the NS sector. Okay, very good. So this is where we are. Now let's solve these conditions. Okay, so we had the condition that the NS sector had to be slow, and we wanted to have a marginal BPS operator in this theories. Very good. So this is where actually the work of Ashok for in the context of D1, D5 was incredibly useful in order for us to basically extract these quantities. So because the modular objects that we're using are very similar to them. So the procedure, I'm not going to describe the whole mathematics. I'm happy to, if you are interested afterwards, I can point to the papers and where things are done and how things are kind of built into. But in 4 steps, this is roughly what happens, and this is why we had to write several papers. So step 1, you select a Jacobi form, so 1 seed. Step 2, you do the symmetric product orbifold and increases the central charge. Step 3, this is where we were inspired by the work of Ashok and his collaborators, is that it was convenient in order to understand how to extract the spectrum to relate this to basically a Siegel paramodular form. It gave us a lot of mathematical control in building and quantifying the spectrum in a useful way. And then the final results, so in the latest papers, we don't describe the whole spectrum. We could tell you not just the large N limit or the large C limit of the spectrum. We can also tell you things about the spectrum at finite values of N. But for the purposes, like what you will be eager to know today is what happens at large N. And this is the final answer that we give to you. So we tell you how many light states in the NS sector are when N is strictly, or when C, the central charge, is strictly infinite. And we write it, well, you can write it as a sum, or we tend to report it as a product expansion, okay? And this is the object on which we're going to impose. This is counting only the perturbative, it's a generating function for only the perturbative part of the spectrum in this large C limit, okay? Yes.
Alejandra, sorry. So how is it that a priori, if you take this number of copies to infinity, Why should I not expect a divergence in this answer?
No, there is a divergence and we removed it. That's why this answer already has the divergence removed.
But
there's
wouldn't that mean that, sorry?
Yeah, if you just grab like the generating functional by itself and you take n to infinity, there will be a very simple divergence, but it doesn't, you can still quantify how many states you have after you remove that pole. So it's
But what does that pole mean? Does that mean that there are infinitely many states at a given conformal dimension?
It's just basically how you normalize things relative to a vacuum state. That's it's like when you compare with the like for instance, when Jan de Boer, like back in '98, compared the spectrum of ADS3 times S3 with elliptic genus on the symmetric product of K3. Yeah, there is this like, it's just, it appears, well, in his context, it appeared from the CFT. When you're computing the supergravity spectrum, you don't like, okay, you're doing a different type of counting, but yeah, it's just basically how things are normalized relative to like yeah, the number of ground states naively will look like it's growing with C, but it's not like, it's just a problem of normalization. Like, and so the matchings take into account removing this divergence.
I see.
Okay. So it's not, there's no physics in, at least.
Okay.
Abhijit, when you take a twisted sector of length n, that has a higher Casimir energy than n copies of a twisted sector of length 1.
Yeah.
So there's no, the fact that you can go to higher and higher twisted sectors, you do that at higher and higher energies. So there's no infinity. It's the Casimir energy that regulates.
Thank you.
Exactly. Yeah. So that's why this answer has that divergence removed, and it clearly kind of like this is the thing that and it's not, this object, just to be clear, it's not counting black holes. This is only counting the perturbative part of the spectrum. Okay, so you go there. So the nice thing about this whole program is that we phrase it basically as like the input being a Jacobi form, and then seeing basically out of this object if it's slow or not. And there's basically only 2 behaviors that you could find.
Sorry, is this Jacobi form the elliptic genus of the seed theory?
Yes.
Okay, thank you.
Up to some unfolding, but yes. So because these things are n equal to, there will be, the examples that we will discuss are n equal to 2, and there's not a charge quantization in the U1. And so the elliptic genera of an n equal 2 theory is related up to unfoldings of the R charge parameter set to a Jacobi form. So yeah, so basically when I say Jacobi form, I mean elliptic genera of the seed theory, yes. Okay, so very good. So there's basically 2 things. If you give me a
Sorry, Alejandra, I think I may have missed it. So you're saying this chi ns infinity, the thing in the box, is the Jacobi form of the seed theory, or that's the final answer?
No, that's the final answer. So sorry. So here I inputted the Jacobi form. So I have a seed Jacobi form. So I pick one Jacobi form and then I do the symmetric product of it. And this is the result of the R going to infinity of when I have this guy going to infinity number of copies.
Okay.
Yeah. So hiding
the formula for F? Yeah, what is the formula for F?
Oh, I didn't write it down, but that actually depends on the seed. So
okay, thank you.
It's a complicated, because it sums over the seed constituents, but this powers up here, this F of HL, are basically, so I can go back, but like in the DMVV formula, it's basically controlled by the parameters of the seed. So, and we give explicit expressions of what these are in the papers, but basically this is where the seed enters. But the thing that we're imposing a restriction on is basically the Fourier coefficient of when you take R to infinity.
Okay.
Yeah, but the input always, like the first thing that you do is select one seed, and then you see how the symmetric product of that seed behaves. And so then based on that, if you tell me what a seed is, you pick one seed, there's only going to be 2 types of behaviors. One is what I will call stringy. So this is the fast one. So the F's, generically what will happen is that they will grow exponentially, where this parameter near 0 is basically less or equal to 1. But you have this exponential growth that is Hagendorn. And then what is more promising, where I can see a slow growth, is that these F actually collapse to Kronecker functions. Basically, it's an improved version of Witten index type. These sums basically are related to some form of a Witten index. And the growth then becomes just square root. And so this is basically gamma equal to 1/2, which looks great. But there's nothing in between. What I want to illustrate here is that you either get linear or you get square root, but you don't get anything. No, there's no other fraction that shows up. No matter what Jacobi form, well, it's a weak Jacobi form, no matter what weak Jacobi form you give me, these are the only two things that can happen to you. Either it's linear or it's square root. And you're done.
And for the usual D1, D5, the answer also is e to the power square root h?
Yes, that's there. Yeah, and that's illustrated in this papers of Jan back in 98, 99. Yes, okay, so those are the two things that happens. And so let's like look now at a space of, so what I'm illustrating in these tables here is basically the space of seeds of Jacobi forms. So what I'm doing in these two columns, I'm listing what the index of the seed is in this column. And this is basically listing the polarity of the Jacobi form. So we basically parameterize the seeds in this way. And the dimension here, this third column, is illustrating how many of them are promising, how many of them are slow. Okay, and what I want to illustrate here is that sometimes we get 0, and so there's no Jacobi forms that will satisfy the criteria. But sometimes we get 1, and we get 2, and we get 3. So there are some Jacobi forms that satisfy, that meet the criteria. Now, what you should basically observe a little bit here is that the space of instances where things are working well is relative. So these numbers here are relatively like small, or they're very few compared to the number of Jacobi forms that you can have at a fixed index t. So at a fixed index t, roughly the number of Jacobi forms goes like t squared. Not exactly, but just so you can have an order.
Sorry, Alejandra, what was B?
B is the polarity. So I'm writing, so if I have a seed Jacobi form, I'm basically writing this as y to the minus b.
Is that, sorry, okay. So that's not related to the number of marginal operators or anything, right?
No, it will be related to the central charge. So B and T will control the central charge of the theory.
I see. Okay.
Yeah. So, sorry, you're thinking of these Jacobi forms as just abstract things, I mean, not related to a particular theory at the moment?
Not at the moment, no, just as a mathematical object that I kind of like, would like to think that it's related to some elliptic genus chi. But at this stage, I don't have to tell you anything about a theory because there's a ring for the Jacobi forms. But
sorry, and what was T, please?
T is the index.
What do you, T,
So
sorry.
the index from the Jacobi form point of view tells you that if you do a shift and set, there will be a face that shows up in the modular.
And in physical terms, is it related to something I know?
It's a U1 level.
Ah, the U1. Thank you. Okay, and this dimension, the output of your calculation was what? What was it, please?
So basically, if you give me, so what we did is basically said, okay, let's look at a Jacobi form of index t, and let's parameterize it by like what is its maximal polarity term. And then we said, okay, how many of these forms satisfy the slow growth criteria? So this last column is how many of them are slow.
Ah, thank you.
I'll be a little bit more explicit, but the thing is that the good point of this part of the table is that it illustrates that we can identify precisely what are the Jacobi forms that have the nice behavior. As I was saying, the number of Jacobi forms is much bigger than the number of positive instance that we find. So that's why we were calling them needles in a haystack, because there's tons of Jacobi forms, but then there's very, very few that meet this slow growth. So it's that's why in previous works, people were struggling at finding other examples besides the example for K3. But
for given T and B, can I ask? For given T and B, do you also allow linear combinations? I mean, how do you test?
I'll illustrate some examples are linear combinations for a fixed. Yeah, so when you have here 2, there are actually physical examples where there are linear combinations of these Jacobi forms.
And the final outcome, the dimension, that's exactly 2, or it's a 2-dimensional space?
It's a 2-dimensional space.
So any linear combination will do. Is that right?
Yeah, we've been like yes. Yes, it's a space. It's not that there's 2 examples.
I see.
Yeah.
Okay, thank you.
Yeah. Yeah, but sometimes they're repeated a little bit. So for instance, this 2 here, it's because you did, so one of the ones here is twice this Jacobi form. So if you do like a phi 0, 1 of 2 set, it will give you one of the bases of the space that you're describing in this 2.
Sorry, Alejandra, you don't require your seed of elliptic genus to have integral coefficients?
The coefficient, yeah, but that still is not like super stringent in terms of like it doesn't tell me that it's still 2. Yes, but it will be any integer combination.
Yes, it won't be an arbitrary linear combination.
No. Yeah, we won't pick like linear parameters, but still, if I say, oh, it's some integer combination of these 2, it's still a space of yes.
Okay, thank you. And just to be totally clear, and sorry for my ignorance, but the space of Jacobi forms with a fixed T and a fixed B is finite dimensional. Is this right?
Yeah.
So you've got a finite dimensional space and you find a subspace in that.
Yes, exactly.
Thank you.
So, okay.
No, sorry. You also impose that the integer should be positive, that there is a positive degeneracy at every.
Oh, well, that's just that always, these guys, it just doesn't matter because there's a reflection symmetry. So when I said that phi 0t had a y to the b, that also has always, it comes accompanied with a y to the positive b.
Loga, it's an index. So
Right.
Index can have negative numbers.
Oh, it's an
So
index.
that's why, like, yeah, so just pick
Oh.
one, like one sign of b, because then the other one comes along
Yeah.
for the way.
No, I was asking about the coefficients, but yeah, as Shira said, the coefficients could be negative.
The coefficients, yeah, because there's a -1 to the f.
Yes.
So yeah, the first one we like it to be positive. So, but I don't. Well, it doesn't matter. But yeah, there's negative coefficients and positive coefficients as you go.
Sorry, Alejandra, I just remedial question. I want to understand why the entries of the 3rd column are always less than the entries in the 2nd column. Is B somehow the overall dimension of the seed, and the 3rd column is the dimension, the subspace dimension of the subspace that works?
Well, the polarity is bounded by. Okay, so let me. There's I'll tell you why that is in a moment, and it will come in the next slide. So let's go to the next slide. So B always can be at most T, because otherwise that's the definition of a Jacobi form as well. The index is basically restricts what is the maximal polarity term. But one of the things that we found in this analysis, and now I'm going to write it in a more CFT language, but it's a mathematical condition that came from this table. As you notice, B was always smaller than T, and that was because there was a necessary condition. There was a necessary condition for having slow growth. So not any value of B and T. So you could already see grossly, you could divide the space of if you fix T, you could basically say, if B squared is less than T, then you will be able to find a weak Jacobi form that has slow growth. If B squared is bigger than T, then there's no hope. And so this basically tells you that the central charge, if we write this in a language of n equal 2,2, super conformal theories, basically it tells you that the central charge of the seed had to always be less than 6. okay? And that's why there's a condition, and the central charge is basically related to this ratio. And so it tells you B squared has to be always less than T, okay? So otherwise, you're not going, otherwise you're always going to find a fast growth, okay? So if B squared is bigger than T, it's going to be fast, and we proved that. So the thing that is nice about this condition, so now we've been talking about the elliptic generis and imposing the slow growth condition on the spectrum, is that this condition that C was less than 6, it came from a condition, so far I've shown it as a condition on the slow growth, but you can also, if you look at the basic condition, basic parts of the symmetric product orbifold spectrum, it will tell you that this is also a condition for you to have a marginal operator in the symmetric product. So it kind of nicely ties that as we were looking at the elliptic genera, we discovered that C had to, C of the seed, so this is a condition on the seed of the theory, not on the whole, but the condition, this condition on the seed was compatible with the condition of an existence of a marginal operator.
So, sorry, Alejandra, the C is equal to 6 B squared by T is some famous formula?
Yeah, basically it's when B and T is 1, that's the simplest case. And that's the 1d5 where the central charge is equal to 6.
Good, yes. And in general, this is always true? Sorry, I didn't understand your boxed formula. C is equal to 6 B squared by T is true for
yeah, so this is our definition of the, so from the elliptic genera,
yes.
Well, I'm basically relating data in the Jacobi form to the central charge of the superconformal theory. That's what I'm doing in this equation.
So this is just a fact about Jacobi forms, that if you have a Jacobi
form.
form.
I relate the Jacobi form to an elliptic genera and assuming that the vacuum state contributes to the elliptic genus.
Okay, excellent. And then that you got that it was less than equal to 6, please tell me again why.
So this is a condition for it to be slow.
And that's requires some detailed analysis, or I should be able to see it from this?
No, it requires some detailed analysis.
Okay,
Okay, the marginal operator is easier to see because there's just a formula on like how the conformal dimensions depends on the twist.
Okay.
And then you can see that C has to be less than 6.
Yes.
So this part is very easy to see. But this one for the slow growth, I don't have like a, oh, sure, obviously this had to be a, no.
Great.
So it took us,
Thank you.
yeah. But it's very satisfactory that they're both the same condition. So we were very happy to see that they were exactly, as necessary conditions, they were exactly the same. But okay, very good.
Sorry,
so,
Alejandra, I don't quite understand. Hello?
Yeah.
I don't quite understand this C less than 6 being necessary condition for the marginal operator. Because if you have a theory with marginal operator, and then let's say, in a very trivial way, you take tensor products and perhaps symmetric products even, I don't know, then the resulting theory could still have a marginal operator, right? In this tensor product,
we just like,
while doing the tensor product, you are increasing C.
Yes. And so that's why
nevertheless, it's going to have the marginal operator.
She means marginal operator in the twisted sector.
Exactly.
Sorry?
It will be in some twisted sector. And so then there's a formula, like you can just start like, so what we did was say, okay, let's say that you grab the vacuum state. Oh, well, not the, like the lowest R charge state in the seed. And you look at what would be the version of it in some L twisted sector. And so if you want this operator to be marginal, basically we got something, okay, I hope my memory doesn't fail me, but if you looked at the twist of a state based on the state with lowest R charge, you got something that it was like, oh, C over 6 times L minus 1. I can look up my paper to see if, I think this was the right formula for a BPS operator. If it's not BPS, it looks like this Renyi type formula that where you get something like, it will look something like L and 1 over L. No, I think if it's not.
If you had a non-twisted sector marginal operator, that's not taking you away from symmetric orbifolds. She wants to move away from a symmetric orbifold. So she needs a marginal operator that is a twist operator. Otherwise, you're not doing what you want.
Okay.
Hello?
Hello?
Hello? Hello?
Yes, I can hear you.
Yeah, sorry, my internet is not very good here.
Okay.
So yeah, I couldn't hear Shiraz's remark. But what I was thinking is that, you know, no matter what twist sector this operator is in, I can always deform by it, right? And these arguments, you know, the motivation of your construction would still be a valid motivation in that case, no?
Oh, I want
Or
it to
not?
be single
I think
trace.
you should said something, Shiraz.
I want this operator
Okay.
to be a single trace operator, and that tells me already it has to be in the twisted sector.
And maybe I could say one more thing if Alejandra, I mean, it seems to me that if you've got a marginal operator that's not in the twisted sector, just in the seed theory itself, then okay, you've deformed the seed theory, but the final result will still be a symmetric product of that deformed theory.
Exactly. It doesn't make the copies interact with each other. Yeah. So in the D1, D5, for instance, there's 80 moduli in the seed theory that are marginal operators in K3, but we don't deform by those 80 moduli. There's actually 4 moduli that are in the twist 2 sector of D1, D5, and those are the ones that we will deform by. So it's in the twisted sector.
Right, you want to move away from the space of symmetric product orbifolds, otherwise you can't get away from this Hagedorn growth.
Yeah,
you have to move away from it.
Yes, so it has to be in the twisted sector, and as well, like something that we will identify as single trace, so that it changes the conformal dimensions of the operators.
Okay.
Okay, very good. It's an hour and a half. I'm really sorry if I'm going over time. I'll be done.
Yeah.
Like, you should tell me how much time I have left. But,
no, I mean, how long do you think you would need?
just a couple of minutes, I think, if I go very quickly. It depends on how many more questions I get.
No, I mean, you can take, you know, if it is, if you are close to finish, then yeah, please do.
Okay.
So don't worry about the time much.
Okay, but okay. Sorry about that. Okay, so sorry. Okay, so now I'm starting to write. So previously we were looking at the space of Jacobi forms and kind of as a way how to quantify the elliptic genera. But now I want to put more physics into this construction, and so this is okay. So what we're going to do, basically, we're thinking that these are theories with 2,2, and basically from that perspective, as I interpret our results, this was the central charge of the seed, and then our condition was that it had to be less or equal to 6. So now, okay, so now we want to actually understand what are CFTs that have this properties, so that we can associate now this Jacobi form to an actual theory, and then ask the question that we have not asked before, was basically the question of the marginal operators. And so the great thing for us is that when you put an upper bound on the central charge like this, you can find yourself in a good situation where there's classifications. And in particular, we know that in the context of minimal models and n equal 2 minimal models, that there's a complete classifications of CFTs if C is less than 3. So not quite up to 6, but at least we can discuss things between 1 and 3. So that seems like a good thing to do. So let's basically do this and search here. And the bottom line of this, of looking at the minimal models is that we found that, so basically I'll put here in as the seed, the minimal model, and then you do the symmetric product of it, okay? So the seed here, the first one is basically an n equal 2 minimal model. And the good news is that all of them, basically you can match it to a Jacobi form, and all of them will satisfy this slow growth condition. So here, let me show you, basically now, again, kind of like this table with now I added the value of the central charge, and let's see what how I'm matching them to various theories. So I didn't make the distinction, just as you can see here, there's some examples with 6, but then there's some examples with less than 3 and so forth. So for instance, 2 examples, since I've been referring to it quite a bit in the past, is the K3 case. So the K3 is basically the first entry for us, where T and B are equal to 1, the central charge of the seed is 6. And so this is our beloved D1, D5 system. This one over here is basically, you can view it, one of them is basically an unwrapping of K3, which, okay, not super interesting. But these other examples here are basically orbifolds of T4 that break supersymmetry. So it breaks the 4,4 symmetry that this case had to 2,2. And they were discussed recently. There's papers by Data, Gabardiel, and Eberhardt that basically computed the elliptic genus for these theories. They looked at the worldsheet theory, they looked at the supergravity, and things look fine. In terms of our classification, there's basically, it's one instance of this, one theory in this dimension 2 space. The minimal models here, I'm listing them. Of course, there's a whole infinite family and it works for all of them. So any minimal model will show up in this list. It's just that I cut the list up to 18, but we proved that any of the ADE classification minimal models will show up here, and here I'm just illustrating where some of them appear. So here's in the ADE notation, here's one, here's another one, here, this one here, then there's an unwrapping of a previous one, and so forth. Very good. And you can see here the values of the central charges are less than 3. Now you can also do tensor products. So if you wanted to go to C bigger than 3, you can also do tensor products of these minimal models, and some of them work. So here are 2 examples of minimal models. You can also, if you wanted to look at theories with C bigger or equal to 3, there's other coset constructions, for instance, Kasama-Suzuki theories, and some of them work. But basically, if C is bigger than 3, we found some examples of CFTs, but we also found examples that didn't work. So there's also tensor products of minimal models that don't give basically slow growth. So not any tensor product would actually do the trick, and not any Kasama-Suzuki model also has slow growth, but some of them do. So here we were just more experimental than for the case of C less than 3. But okay, but now I wanted to just say a little bit about the moduli space. So we had in mind that here we had the symmetric product, that's a weakly coupled point, and that we were adding this marginal deformation to try to go to this strongly coupled point. And so from that point of view, so while a marginal operator basically has this conformal dimensions, and the ones that are supersymmetric, we're basically thinking of them as basically this fermionic generator acting on an on a chiral primary with charge either Q equal to plus or minus 1. So we're basically looking for chiral primaries with this R symmetry charge. And that will give us, after acting with G plus minus a half, will give us the marginal operator.
Sorry, just one question. So
Yeah.
in these examples, the marginal operators are unique, or do you find many marginal operators? Or?
Sorry, if I find what?
Is there a unique marginal operator? Let's say if I take one of your example, like
They're not unique.
Oh, okay, you have it here. Okay, sorry. Yeah.
Yeah. So this is basically all the marginal operators that we found. So here are so this is for the minimal models. So when C was less than 3. And this is basically, we know the spectrum of all, basically all the chiral primaries. They're very nice formulas that I written down here. This is basically the generating functional for the half BPS states. This is basically the condition that we're looking for Qs that meet this criteria. And this is basically the final result. Okay, so for the ADE classification, you get moduli in the untwisted sector, which is not super interesting. There's a bunch of moduli in the twisted sector, and then these are the ones that are single trace. Okay, so here there's a bunch of them that are multi-trace and single trace, but if you just want the single trace ones, these are the ones. Okay, so depends a little bit on the theory. Sometimes you just get 1, but sometimes, I don't know, here you have 4, here you have 3, and it depends on the theory. But what is interesting to note is that you also have this, you have more in the twisted sector, you also have multi-trace deformations. So I just wanted to then make a comment. So there's basically 3 comments that since I've been talking a lot and quite fast. So comment number 1 that I want to highlight here is that if the central charge goes between 1 and 3, our classification of, like, from the point of view of n equal 2,2 theories is complete and exhaustive. And it basically is this ADE minimal models state. And what's very interesting that is happening here, so the first point of interest is that the elliptic genus is slow. And every time that we find that the elliptic genus is slow, there's also this marginal BPS operator. Okay? So you can view it as vice versa as well. There was a marginal operator and the elliptic genus was slow. The elliptic genus is slow, marginal operator. Now, the other thing that is interesting is that there are both single trace and multi-trace operators. And so the multi-trace ones can actually change the couplings in this putative strong coupling theory. So that's kind of interesting to explore. What would multi-trace?
Sorry, the multi-trace ones are products of 2 twist operators?
Yeah. So there will be like 2 twists, like if you have single traces that are combined, and that's what I will call multi-trace.
So for instance, one twist that connects 2 strands and another twist that connects 2 strands.
Exactly, yeah.
Thank you.
Yeah, and we have them in the appendix of our paper, we kind of list them in more detail that I'm listing in this table of, like, what are the combinations that come in. Now, the other thing that is interesting, and I want to contrast it, is that for C, so if now I'm between...
I'm sorry to interrupt, but these deforming by these, you would think of these, I would imagine that you would think of deforming by the single trace operators as getting your gravitational theory, and then deforming by the multi-trace operators as a deformation within that gravitational theory.
Yes, yes. So I always will need the single trace one, but the thing that is fun is that I can also add these multi-trace ones and see, yeah.
And that you should be able to see in your purely gravitational theory once you have it.
And what are the effects? And it can make this, the gravitational theory, like, strongly coupled and things like you can have like a strongly coupled version of a gravitational theory. I think it hasn't been, there are some papers that discuss the effect of multi-trace operators, but I don't know how, like, yeah. I think it will be interesting to explore what are the effects of these multi-trace operators and how we understand, like, the gravitational theory in that context. Now, yes.
So are all these multi-trace operators just double trace, or you also get more?
For sure, double trace. I can check. I think there were more. No, I think there were more than just, yes. Let me see. I think I have, this is the nice thing of doing talks online, that I can go look at my paper. I'm pretty sure, but I don't want to. Yes, there's 3 and 4. Yes, there's it doesn't have to be necessarily.
Okay, and one another question: when you have more than one single trace twisted moduli, do you understand whether there's some symmetry reason for it? Like maybe it's just more supersymmetry than what is put in, or something, or
they're all 2,2.
But sorry. Yeah, but you're also counting things like 4,4 inside 2,2, right? I mean, so, or
well,
whether there's some rationale for having more moduli, or it's not.
I don't know. It's interesting. I don't know. It's because we don't have that many. Yeah. To be honest, I don't know.
I mean,
I don't have an intuitive reason why. Like the thing that I can say is that the seeds of any of these minimal models did not have a marginal operators. They only had relevant operators.
right.
Sorry, maybe a related question. Your operators, do they are they operators such that their scaling dimension is some multiple times the R charge?
Is the scaling dimension?
They're supersymmetric operators. They're
Yeah, they're supersymmetric, so they're controlled by the R charge.
right. So the scaling dimension is equal to the R charge.
Yeah, divided by 2. But yeah.
And then when you get multiple operators, they then therefore have the same. Since they're all marginal, they all also have the same R charge.
Yeah.
Okay.
Yeah.
Thank you.
But okay, but the thing that I wanted to note, so I was showing to you some examples of like tensor products of minimal models where you still have C less than 6, and there's this Kasama-Suzuki models as well that you can also explore a little bit the range between 3 and 6. But the thing that we noticed there was that there were, so you can find, there will be examples, so within the space of theories that we could try to quantify, there were examples that were fast, and there were some examples that are slow. But within the fast examples, we did find examples that you had there existed, not always, but there existed a marginal operator. And that is BPS. And this basically tells us that the requirement that you have a marginal operator does not necessarily imply that the elliptic genus will be slow. And so it seems from our observations that this condition is stronger than this condition, because we do have a counterexample where you have a marginal operator, but it's in the fast category. So in terms of like what implies what, from this scenario, it seemed that I just had to impose one condition and then I got the other one for free. But from this range of parameters where, okay, we don't know what all the CFTs are that live in this range of parameter, but we do have a counterexample where there is a marginal operator, but the growth is Hagendorn. So it will be interesting to see this. I take it as a very interesting example to notice what if you start doing conformal perturbation theory and try to see what is the effect of this marginal operator. It probably means that the effect of this marginal operator in this case should be different from a case where I have slow growth in terms of how it would be starting lifting the anomalous dimensions and so forth. And this marginal operator, just to be clear, was a single trace marginal operator. So okay, so I reached the end. So basically, so now I can, yeah, an hour and 45 minutes. I'm so sorry. So starting to conclude, so what happened to us today? So what happened to us today was that we were trying to.
I wonder whether your slides are frozen. If you can.
Oh, let me. My slides froze. So you could see. Okay, can you see them again? No.
I see the summary. Is that what you want to show?
Well, let me. Can you see the slide that says moduli? No. Okay, I'll stop sharing and then I'll share again very quickly. It says that sometimes it does this. Okay, now you can see.
Yes.
Oh. Okay. Yeah, but now you see it with the. Okay, doesn't matter. You see my toolbar. It's fine. Okay, anyhow, we're basically at the end, so it's fine. Okay, so the summary basically just to we're wrapping up now. So hopefully what I told you, what I wanted to convey today is basically try to understand from the space of symmetric product orbifolds, what is the intersection basically with the holographic CFTs. And the two conditions that we were imposing was having that the perturbative regime was slow growth and the marginal operators, and there was a BPS marginal operator. And basically I gave you a whole infinite family of CFTs that meet these two criteria. And there is, and the infinite family of CFTs that I give you was basically symmetric products of n equal to minimal models, okay? Plus some other examples that you would have recognized from K3 nonlinear sigma models. But basically, this is what we were able to provide. So there's a classification of the overlap. In terms of Jacobi forms, there's a complete classification of the overlap. In terms of CFTs, only up to central charge equal to 3, we will be able to give you a complete classification of what are the theories that meet these two criteria. Now, if you ask me, what are the next steps? What comes next? Oof, everything. Absolutely everything comes next. So I focus on the approach of this talk, although I started talking about gravity and what were conditions on gravity, we then very quickly focused on the CFTs themselves and trying to impose this set of necessary conditions on the spectrum. So of course the question is, what is precisely, so if I give you one of these ADE models, what is the gravity dual? What is the string construction? What is the D-brane description of this of the system? That today, I personally don't know. I would also like to know how to describe the CFT at strong coupling. So these are really, like I want to emphasize, they're necessary conditions. You could very well question if they were sufficient. Maybe having these two things does not guarantee that I have a good strong coupling point, that I can actually lift to arbitrary, have this really true separations of scale between the string length and the ADS scale. And say yes, I have a theory where I don't have additional currents, everything there's a big delta gap in the spectrum, and I can have actually a local effective gravitational description at low energies. So there are necessary conditions, but it's not clear that they're sufficient conditions. And I think that's quite important in trying to understand how ADS-CFT works. What are the set of sufficient conditions? When would you have said, yes, this, you impose all the necessary conditions, and then everything else that we understand will come basically for free. We won't have to impose more restrictions on the conformal field theory. So, but okay, but that's what we have behind today. And basically the idea of this type of searches is to understand what is the mechanism behind ADS-CFT. So what makes it work, and actually how big is these spaces, or well, how big is this green region? So what are the space of CFTs, and what does that tell us about quantum gravity? What are effective theories of quantum gravity that have a nice UV completion? So with that, I hope one day that will open all of our doors. So I'm done now. Thank you.
Okay, Abhijit is here.
Let's thank Alejandra for a very nice talk. Hello, questions?
Alejandra, maybe I can start with something probably vague. The string dual description for the D1, D5 system was ADS 3 times S3 times T4.
Times K3.
Let's say we had D1, D5 wrapping T4, or
okay.
K3, it would be ADS 3 times S3 times K3, right? Okay. So now, and there we got a sigma, we got a symmetric product of sigma model on K3. So with that analogy, it would be natural to suggest that somehow your string dual description of your models is ADS 3 times something times minimal model. Is this what you suspect, and what could that something be? Yeah,
the thing, so this is why it's not super easy to figure out what the dual is. So yeah, so ideally, it will be something where the minimal model somehow describes the moduli space of what would have been the K3, quote unquote. Now, one of the problems that we have, even identifying what the dimensionality of those spaces are. So for instance, in the case of the example that you were giving, you would want to, so the K3 is kind of has fixed size, and so what you focus usually is on the ADS 3 times S3, right? And the 6 dimensional description of this theory, because both the ADS and the S3 have comparable sizes. So here we can't tell what the dimensionality of the space is. So we know that there's an ADS3 factor in the compactification, but it's very obscure what happens to the rest. And it's because we don't have enough supersymmetry. It's because a lot of these examples have only n equal 2. So usually, for instance, in the case of n equal 4, you would have said, how did you discover the S3? How did you come about to knowing that if you started with this nonlinear sigma model on K3, how does the S3 come about? And usually the lore is that the S3 came from the R symmetry. It's the geometrization of the R symmetry. So for n equal 4 theories, you have SU2. And the SU2, you have 2 copies of it. And then those 2 copies, you associate them with the S3 symmetry and the geometry. So now I only have 2,2, which means that I have a U1 on each side. And that's not quite stringent enough, like to tell me what is the geometrizations of those U1s. It's too little.
But does it tell you that there are at least U1 times U1 current algebras and that whatever?
Yeah, but it's not enough. And so usually what people do when they try to break supersymmetry in this context, it's not, it's not that easy to obtain. So for instance, one of the examples that I gave, this T4 mod G, that broke the 4,4 to 2,2, but it still make the central charge be 6. So it didn't change the orbifolding doesn't change the value of the central charge. So that's one way. So you can, and then that tells you, the 2 SU2s got broken down to U1s. But in general, that's the thing. And the supergravity constructions, it tends to be difficult to categorize or classify all of these like geometries because they tend to come from breaking the S3 in some way. So you usually, not always, but it tends to be convenient that you start with ADS3 times S3 and then you do something to that to kind of like break down like the number of supersymmetries. And so that's why a lot of times people get like 0,4 because you break supersymmetry completely on one side. But besides this example of T4 mod G, I don't have any other supergravity background that has 2,2.
But suppose you just try to construct it by hand. Would you?
They're circles, and so then I don't, and those doesn't give me curvature to balance the ADS curvature. Too little.
Right, so it would have the circles would have to be part of a squashed sphere or something like that, right?
Yeah, so that's why, and then you know that it's a non-trivial compactification because, yeah, I can't write like ADS3 times S1 times S1 because that will not solve any like supergravity like equation. And if I put S2, then I already have an SU2 somewhere. So then it's
but one hint is that the central charges have to add up. So if you agree that the one of the factors is your minimal model, then that tells you what the net central charge of what remains has to be. And I was wondering whether you could just, I don't know, do some guesswork and try to get, okay, it's a very vague question.
Yeah, it's a little bit big. So the thing that I wanted to do was when I wrote down this, so I'll just write it here in this slide. So when we wrote this chi infinity, that was the sum of like the NS sector at infinity. I wrote it in a very CFT way, but I could try to write, so there was this nice product formula that had like this Q's and stuff and the F here in the top Y's, okay. These powers here basically contain information about like the multiplet content in the supergravity theory. So it will tell you, roughly speaking, how many vectors, how many hypers you have, because they will come about like from a gravitational point of view of doing some second quantization on their perturbative fields. So one thing that I was trying to think about, like, okay, maybe let me write this formula in a way that it looks like basically a second quantization of single particle states in gravity. There will still be some assumptions that maybe I have to put into what I think this supergravity in three dimensions organizes itself like. I hope I don't have to input too much, but that could be a way how to try to kind of understand a little bit, at least from a three-dimensional point of view, what is the content? How many gauge fields do I have? How many scalar fields? Because one thing that you might worry, like you don't want the number, although everything here I was imposing that it wouldn't, these are all states that are not Planckian. I still don't want to have, for instance, if I take in the ADE models, there's a K parameter. I don't want to have, if I take K to infinity, I don't want to have basically infinite number of scalars, because then it will start looking again a little bit like this, as you were asking me at the beginning, like it will look like I have an infinite number of fields in the bulk, and that will start being problematic as it might start competing with G Newton. So having a little bit more control on how these powers here basically control the supergravity spectrum might tell me a bit more if I will have some obstructions on building those gravity duals, and maybe there's an upper bound on the K that parameterizes the minimal models. But then, yeah. So there's some hints that we have about how to construct effective gravity dual.
One question, Alejandra. In the requirements that you mentioned for the emergence of semi-classical gravity, maybe I missed, but one requirement should be that the chiral algebra does not have spin-3 currents, right? So no W symmetry, only Virasoro and some current algebras and so on. Is this something that can be imposed by analyzing the elliptic genus?
The elliptic genus, the problem, there's a little bit too many cancellations. So I think the elliptic genus will not tell you if this currents survive or not. So on the symmetric product, there are currents.
You mean the W currents?
Yeah, yeah, there will be current, because there's actually, at the symmetric product point, which is this weakly couple point, as you look at the, so the seed doesn't have currents, but the symmetric product itself will build up currents, conserve currents, because it will look like a stringy spectrum where you will have higher spin states and they will all be conserved. So it will look like that's why, like in the work of Matthias and Rajesh, like they have like this higher spin type flavor of understanding them. So it's not clear what W symmetry they have, but it's some W infinity symmetry that the whole like symmetric product theory contains. And the hope is that these currents get lifted. So as you move away from the symmetric product, they will acquire masses and they won't be conserved anymore.
But if that is the case, then the index sees this, right? Because index precisely looks at things that do not get lifted. So if you don't see them in the index, it's reasonable to assume that it gets lifted.
It's too weak because there's a -1 to the F. So you just know that some differences are canceling.
No, I'm just saying that if there is a mechanism that lets the higher spin currents to be lifted, then even if you compute the index at the symmetric orbifold point, you should be able to see that there are no currents. You know,
it's too weak as a condition. That's my point. You don't see them in the elliptic, okay, yeah, no, because I see what your point is. It's like you could have said, did the currents already contributed to the elliptic genus, right?
Yeah, if they were not lifted, then you would see this, right?
Well, but it's just that it's not a guarantee. That's my point. So like you can say, well, in the cases that you had Hagendorn, clearly these things were not lifted because roughly the elliptic genus is growing basically at the same rate that the whole partition function is growing. So all the states are still basically there. Now, if they don't contribute to the elliptic genus, because it could happen that it happened that the objects were such that the -1 to the F made them drop from the elliptic genus, it still doesn't guarantee to you that they get lifted. That's a thing.
No, but sorry, I mean
it just tells you that they don't contribute to the elliptic genus. That's only
one of your requirements is that this elliptic genus should grow slowly, right?
Yeah, but
and
it's
that's
not
because you're requiring that there are no stringy, there are no stringy towers. But I'm saying things could be partial. In that, a whole bunch of things are lifted, but let's say spin 3 is not lifted. Something like that could happen, and that
Yeah, exactly.
this is something that should be visible, I'm saying.
Yeah, and so that's why you would look at then how this, so what we're hoping is that, because we like, and this is one of the next computations that we want to do, is that, okay, so we need to make sure that these currents are getting lifted. And that's the role of the single trace operator.
I think your condition that the Hagedorn growth should not be there means that, you know, all infinitely many currents must be lifted, but that doesn't necessarily rule out finitely many currents not lifting.
Yeah, so actually there was a paper recently, a couple of weeks ago, by Samir Mathur and one of his collaborators, because even like in the 1D5, like I think it hasn't been fully explicitly checked that all the currents get lifted. So he had a paper a couple of weeks ago, like showing like first, like he was trying to argue that this had to be the case for the 1D5, that things were getting lifted, but it's just that it's not, it's what you're saying is natural. Like, it's like, yeah, that kind of makes sense, but it hasn't been like proven in a rigorous way for me to be completely confident to tell you, yes, everything here is going to get lifted. Because in some sense, there's another issue. You could say, okay, things are going to get lifted, but maybe they don't get lifted parametrically with a coupling. It just flattens.
Yeah.
So it gets lifted a little bit, and then it kind of like, it gets stuck.
That of
like,
course
so
the index will not help you with.
Exactly. And so then what, like, then it's still not good enough. And so you really like want this thing to grow, like as you take the coupling to infinity, that these things really go like up to infinity.
Yeah.
So, and that's very hard to establish because you're doing it by doing perturbation theory, and that's, I even in n equal 4, I would like to know a bit, like, I think, yeah, you know much more about n equal 4 super young males here, but I think like if you were a purist from the point of view of super young males in 4 dimensions, and you would tell me like what is the strongest evidence that you have from the point of view of the CFT that the anomalous dimensions all get lifted arbitrarily. I don't know if integrability has actually solved that. My impression was that it was no, that you just see that the things tend in the right way from each side as you do the weakly couple like point to the strongly couple one, or not?
Sorry,
or maybe,
but they did, I thought they had a full function of lambda, and you can actually see the.
But for all operators?
No, operators which don't grow with n, and so small operators in some sense, yeah. But I thought, like at least not like determinants and so on. So, but I thought, like things that are accessible to integrability, they can get a function and they can actually.
And they can look at it for any value of lambda at large.
Yeah, at infinity.
Yeah. Okay.
And then
it might be then. So. Is this related, just so to complete my, is this related to the results of whom, of Silvio, or am I in the right ballpark or not?
Staudacher-Beisert comes to mind.
Okay. Yeah, because I was trying to understand a bit better, that this is part of my homework, to understand better how these things are established in super young males, to know basically how much I can say in this context, because I thought that only that this was something like, okay, there was way more knowledge in n equal 4 super young males, but it was still not maybe to the level of saying like, oh yes, we can fully establish that everything gets lifted. But
sorry, could I ask what's probably a very stupid question? Are there any degeneration limits of K3 that reduce to some sort of minimal models?
not that I'm aware of. Maybe they are, but I don't know. That's my short answer. I'm as ignorant as you, Shiraz, on this. So.
Yeah. What are these? Sorry. Okay. Yeah. What are these Gepner points? What happens at these Gepner points? I'm sorry to be so ignorant.
But I'm not sure at those points the number of supersymmetries gets reduced. No.
Gets reduced to me.
Does it get lower than 4,4 at those points?
No, I think it would just stay wherever it was for K3.
Yeah. So then it won't be, because the minimal models have 2,2 and they definitely don't have 4.
But I was wondering if you went to that point and then did some sort of orbifolding that reduced or something like that.
Well, that might be similar to what this paper, but then the central charge also didn't get reduced by the orbifolding. It's still C equals 6.
Yeah, so it could be like a sum of 2 minimal models. Okay, I'm just right.
Yeah, so that you can do. You can have like some of these tensor products that I was describing that can go up to C equals 6. And yeah, and then maybe they correspond to some special point in this other nonlinear schema model. But the ones that are truly like 2,2 with C less than 3,
Okay, yeah, thank you.
Another observation is that the minimal models admit a coset description, right? I think it's some sort of an SU2 times U1 divided by SU2 or something like that. I forget exactly. Yeah. But this is something that could nicely fit into the background, perhaps. I don't know.
Perhaps, yeah, maybe viewing it from the coset point of view, yeah. So for like they're a special case in what people call this Kasama Suzuki, like it's one of the values in that construction. And yeah, it might help trying to geometrize this thing.
Hello. So Alejandra, can you tell us more about what is the data that is on the gravity side? For example, in the massless, just the massless spectrum on the gravity side, from this Fs that you have, like do they vary very much as you vary over the ADEs, or?
This is part. So they depend a little bit on K. But the thing that yeah, they have some dependence on K, but like I haven't fully, like we have them tabulated. So if you, like in the appendix of our last paper, we just like kind of went and wrote them down, all of them. And they have some K dependence, but the thing, I have to just be a little bit careful how I associate that with the supergravity spectrum. That's all. And they did not grow with K, at least when we looked at it. So we did it for the half BPS one. So not for this F that I have specifically here, but for we did the computation for the half BPS operators, and those powers don't grow with K.
So even the massless fields in the gravity,
they seem to be like bounded still, although you can take K to infinity. The number fields seem bounded, but I want to do it more carefully so that someone that knows more about, like, so as we kind of try to understand, okay, what are consistent supergravity constructions, like kind of how to match these things in it. But at first look, they seem to not grow with K.
Okay, that was the next question I was asking. So let's say I give you a supergravity theory in ADS3. Would you be able to like distinguish between the ADs, like just by looking at the massless spectrum? Like, is the dependence?
You can almost, yes, I think I will, yes.
Okay, just from the massless spectrum, you know, they tell you that.
Have to make sure that there's no degeneracies in these chi infinities, and I believe that there's not, unless naively it seems like the chi infinities that I associate for every ADE is distinct.
Yeah, but that is the full, you know, like all the Fs. But I'm asking whether I can give you just some Fs. How many do they give you in order to, like, for you to distinguish?
That I don't know, but it's a great question. Yeah. What is the minimal set of these powers that I need to, yeah, I don't, yeah. No, okay. We haven't analyzed yet this in terms from that point of view, but yeah, that would be.
Okay.
Yeah.
Thanks.
Maybe I could make a little comment. You know, the program that you're related to something Loga asked earlier. the program that you're studying has a three-dimensional analog from for supersymmetric Chern-Simons theories with matter. Once again, there you could ask how the superconformal index grows, whether it's hagedorn-like in the low temperature phase or not. And there, as you are finding, there also this question was looked at for arbitrary matter content for simple theories with, let's say, 1 or 2 gauge groups and matter in the adjoint to the bifundamental. And there also, basically, you found that almost every matter content led to exponential growth in the index. And there were very few exceptional cases which did not lead to exponential growth. And then all of them by now have known supergravity duals. So wherever it worked in that situation, wherever the growth was sub-exponential, every case, without exception, turned out to have a supergravity dual. 1 or 2 of them were hard to find, but they were eventually found.
Mm-hmm. But were they, yeah, I guess, yeah, that will be ideal, like in this context as well, to eventually argue that all of these examples will have a.
Yeah, but it was a much more controlled set there. There were like, there was ABJM and it's sort of like orbifolds. And then there was 1 or 2 more, maybe really in some sense only 1 more. And then that Jeff Harris and collaborators a few years ago found the supergravity dual of that one. It was open for a few years. There was this theory which had a low energy spectrum that was power law-like, like supergravity-like, but nobody had a description of what the theory was. And then Jeff Harris and collaborators found that a few years after. So that's I mean, if you take, of course, it's just an analogy, but it suggests that perhaps you should be able to find supergravity duals for all of you.
No, I'm hopeful that it will be the case, because I also want to just know if, like, yeah, and from that point of view, like saying that we don't have Hagedorn, was that enough or not? And that's, I think it will be very nice to establish. But yeah, we have like very little intuition of like what is the version of ABGF in this context, and so it's like I'm a little bit. My problem is that I'm a little bit clueless on what ansatz to write from a 10-dimensional point of view.
So Shiraz, in the statement that you said, what was the amount of supersymmetry that was assumed?
Just n equals 1, basically. I mean, it's same amount as n equals 1 in 4 dimensions. So 4 supercharges plus supercontrol. Yeah. So that's probably the same amount that she has.
Right.
2, 2 is 4 supercharges, right?
Right.
Yeah. Yeah.
Yeah. So yeah. So there it was just very easy to do. There's just like Alejandra has the simple Valende and Valende formula. There's a simple formula for the superconformal index in terms of an integral over holonomy matrices. Then you can just analyze that integral, and typically it grows faster than Hagedorn. It undergoes the Hawking-Page transition even in the index. Very few cases it does not. You can just classify them, at least with 1 or 2 gauge groups. If you allow the number of gauge groups to proliferate, there may be more.
Okay. So do you which reference would you recommend to look at that computation in 3D?
Embarrassingly enough, it's a reference that I'm involved in. It's a paper I wrote with Yin, Tarun Sharma, and Prithvi Narayan about 10 years ago.
Okay.
I can't remember the name of the paper.
No, that's fine. Okay. But no, I'll take a look at it, because I wanted to understand a bit better what were like analogous versions of this in the higher dimensional point of view. So no, that's very interesting.
In that case, for the one case where there wasn't a known supergravity description, just like you said, like you're saying, we wrote down what the spectrum of the supergravity theory had to be. And then we posed it as a challenge for somebody to find it.
Exactly.
And somebody found it.
Yeah.
By the way, Alejandra, so another kind of related comment is that, this question that I asked about the higher spin currents. So we had done once a similar calculation in 4 dimensions about with an n equals to 2 superconformal theory. And the index, because we could just compute it order by order, we were not able to look at things such as growth and such, but we were able to look at whether they come from higher spin operators, and we did indeed find some higher spin operators in the index, and that kind of ruled out the hope of there being a purely gravity dual.
So you established like that the higher spin currents contributed to the index.
Right. Yeah. So even without looking at the growth, only this observation was somehow. So that's why that's what motivated my previous question about the currents.
I see. No. Yeah. From our point of view, we can't like. It's like, yeah, like the thing that we can say is that they don't contribute to the index, but yeah, it was still not enough guarantee to assume that it was going to be slow growing. So, but yeah, no, that's interesting to know. Thanks.
More questions? If not, let's thank Alejandra for a very nice talk again.
Thank you all for logging in for so long. More than 2 hours. Thank you.
It was really great, Alejandra. It was very clear and very interesting. Thank you so much.
Yeah, thank you.